In this example, we are asked to prove that the following proposition is true. 1 times some number plus 2 times that number reduced by 1 plus 3 times that number reduced by 2, and so on, until you come to that number times 1. If you sum up all those terms, then the proposition is that you will get n times n plus 1 times n plus 2 over 6. So whenever we're given something of this form, it's always it's hinting to us for all integers n greater than or equal to 1 that a nice technique is to use induction. So let's start with n equals 1. So that just gives us 1 times 1, which is 1. That's as far as we'll go. Now let's check the right-hand side. The right-hand side gives us 1 times 1 plus 1. It's 1 plus 2, replacing n with 1 is 6. We'll just work a little bit this way. 1 times 2 times 3 over 6, which is 6 over 6, which we see as 1. All right, so we've shown true for n equals 1. Now in induction, our next step we will do is called assume, not called, is when we assume that n equals k is true. All right, so we're going to assume that if you have 1 times k plus 2 times k minus 1 plus k minus 1 times 2 plus k times 1 is equal to k times k plus 1 times k plus 2. All right? And divided by 6. So we're assuming that this statement here is true. And what we're hoping is that when we do n equals k plus 1, that somewhere along the line we're going to be able to make this substitution. And that's where this hint is going to come in handy. Now let's carry on. So we're going to attempt to show n equals k plus 1 is true. All right? So everywhere there was a k, we're going to put a k plus 1. All right? So instead of 1 times k, you have 1 times k plus 1. And then instead of 2 times k minus 1, you're going to have 2 times k plus 1 minus 1. Plus 1 minus 1 is just 2k. And we keep going on in this fashion till we come to the end. And instead of k plus 1 minus 1, you have k times 2 plus k plus 1 times 1 to end. All right, now the goal, the right-hand side, is that you have k plus 1 times k plus 1 plus 1, which is k plus 2, and k plus 1 plus 2, which is k plus 3, all over 6. All right, so this is what we want to get to. K plus 1, k plus 2, k plus 3, all over 6. And this is where we're starting. All right, remember this hint here. Right? What you can do is you can take something of this form, all the way up to 6. In this example, we're going to go all the way up to k plus 1. You could reduce it by 1, and just don't forget that in the end then, you'll have to add this bit on here. So let's do that. Instead of a 6, I could write a 5. Instead of a k plus 1, I can write a k. So 1 times k. Plus 2, instead of a 5, I can put a 4. So instead of a k, I put a k minus 1. And I carry on like that. Instead of a k, I have k minus 1. And instead of a k plus 1, I simply have k. Now, don't forget, we've got to add 1 to 6 in this case. So I need to add 1 plus 2 until I get to k plus 1. Okay, so the beauty of that is what I can do now is I can take all of this here, right? And it looks familiar, doesn't it? We're assuming 1 times k plus 2 times k minus 1 plus all the way to k is k times k plus 1, is like this piece right here. So let's put that in. So k times k plus 1 times k plus 2 all divided by 6. Now I need to add this piece here. This piece here should look very familiar to you. You're adding up all the numbers from 1 to k plus 1, and you're doing that. This is a story I told you guys about Gauss. So you're doing that. It's summing an arithmetic series from 1 to k plus 1. So let's see what that's going to do. So there are k plus 1 terms. And when you add the first term, u1 plus un, you end up with this. So the first term plus the last term multiplied by how many terms there are divided by 2 will give you the sum of an arithmetic series. So what we're hoping is that when we combine these two things and simplify, we get the goal. Let's have a look. So k times k plus 1 times k plus 2 over 6. Not much we can do there, but here, let's make a common denominator. So we'll multiply top and bottom by 6, and we'll end up with 3. 3 times k plus 1 times k plus 2 over 6. All right. Now you have a common denominator, but we also have something else. When you look here, you have k plus 1 in both places. You have k plus 2 in both places. So you have two binomial common factors. Let's factor out k plus 1, factor out k plus 2, and what you're left with is k plus 3. So as soon as you factor that, and of course 1/6 factors from both terms as well, you see that you've arrived at the goal. So the left-hand side now equals the right-hand side, what we wanted. So therefore, since n equals 1 is true, and n equals k plus 1 is true whenever n equals k is true, the statement, or I think they call it the proposition is true for all n greater than or equal to 1.